In this talk, I'm going to talk about our project funded by CCI on low-cost soil moisture sensing using Wi-Fi signals. So our project is motivated by the fact that we will need more food production, agricultural food production by 2050, and this is mainly due to the population increase, and there are technologies mainly around the precision agriculture concept, which aims to use the technological advancements as well as like various sensor data collection to optimize this increase in the yield, increase the yield in the field, or reduce the resource consumption, and then also eventually enhance the sustainability. So since we are focusing on more on the water usage, which is actually in agricultural water uses 70% of the world's fresh water, any type of optimization that will reduce that will help that will help us to reach out this goal of increasing the food production. And we are mainly focusing on more smart irrigation and fertigation based technologies, which is mainly done by technologies like this one, which is variable rate irrigation. And the idea in this one is like if you have seen one of these in the crop fields, which are called central pivot irrigation systems, which are basically rotating around the, like a central point with the pipes turning around that in a circle, and then also applying different irrigation amounts for different regions of the field. The goal of this system is basically to optimize the beneficial use of agricultural water, and of course, it also comes with other benefits, which is reducing the energy cost because there is a pump over here, and then which is making that system turn around. With a single pump, you can cover with a single pump and also minimize energy usage. You can cover the irrigation of the entire circle region over there. So, but in these systems, like we need input from the field, meaning that there should be some sensor readings, which is actually telling us what is the soil moisture in currently in the field and what amount of irrigation is needed for every part of the field. As you can see, like they use what we call prescription maps over here, which basically gives us that input. But these prescription maps are actually obtained by using sensor data deployed at different parts of the region. And then since there is no high dense deployment, the in between areas are actually extrapolated by the available readings from the sensors deployed. The traditional sensors actually that tells us what is the moisture amount in the soil could be classified into direct methods as well as the indirect methods. In the direct methods, what the methodology is basically you basically take out some soil from the environment field and then put it to oven and then dry it up so that you make sure that there is no moisture in it. Then you take the difference of the weight so that you can understand the actual moisture amount in that soil portion. But as you can imagine, this is a destructive method and it requires a lot of work and it's not gonna work in real time. While this is the ultimate, ground truth, it will not be able to help us to obtain this type of map in real time. That's why in current systems, this is actually not done in real time. It's basically done, seasonal, so that you can just rely on the current readings every time, whether it rains or not. You cannot just understand that difference. Since this method is very costly in terms of the amount of work, there are other methods that are used in different sensing technologies, and which basically called indirect methods, and they rely on some other features correlated with the soil moisture, like the soil tension, capacitance, resistance, things like that. And then, but these methods, again, as you can see, like in different pictures over here, they also use different equipment which can be highly costly, especially this radar-based technologies, ground penetrating radar over here. It needs to go over the entire area so somebody needs to move that, and you to be able to get a real-time measurement from this will be also hard work. And all these methods will not share the high cost, as well as not being able to give very real-time data in an accurate way. So motivated by these, actually, our project aims to develop an alternative solution, which is gonna use Wi-Fi signals between a transmitter and a receiver. And as the signal propagates from the transmitter to the receiver side, it goes through this soil environment, which has also the moisture amount and different water amount, right? It also comes with other different features as well, like soil texture, and like maybe there's a rock here, right? So all other obstacles will affect that. But overall, it will be able to carry us the information of the soil when it's received by the receiver. So once it's received, with doing some signal processing of the received channel state information, while also some removing the anomalies and feeding it to a machine learning model, our goal is being able to predict what's the actual moisture amount in the soil by understanding that correlation of the signals, propagation characteristics, as well as with the soil moisture. But this system is different than the previous ones, like that use radar over here, which has the both transmitter and receiver, as well as it uses a different frequency. And this one we use Wi-Fi, which is ubiquitously available. That means there are a lot of already low-cost devices, which are, like in this one you specifically see a microcontroller, which is less than $5, and which lets you send it the Wi-Fi signals to the other side up to some distance, of course. I will talk about those limitations and things like that. And also these can run, like very long time. Let's say if you measure just 1 minute of data on the receiver side and put them asleep and make them work just a total of 1 minute during a day, they can last like 6 months in the field. So, and also since we measure, the soil moisture for the soil in between these TX and RX devices, there will be, of course, other factors, let's say the soil texture, as well as the distance between the TX and RX, what's the depth of their installation, will all affect that results. That's why we'll look at the effects of those factors as well. And also, like, since we are using Wi-Fi, we can also kind of merge all of these, like many deployments of TX and RX devices in the field, where they can sense between each pair of TX RX device the soil moisture amount, as well as they can also send the collected data through the Wi-Fi to other devices, and then which so that you can collect them in a central point. So with all these, our goal is being able to develop those prescription maps, which can be used in VRI systems, so that we can get a real-time soil moisture situation in the field, and then irrigation, the efficiency can be optimized. So let me give you a little some brief background on the Wi-Fi sensing and what kind of data we collect. So Wi-Fi operates in OFDM. So meaning it is divided into small subcarriers, and in this case we use like 64 subcarriers, and each of them uses different frequency, and each of the frequencies, each of these subcarriers will be affected by the environment differently. So their amplitude and then the phase information will be affected depending on the frequency they are running on. So they are not just going to be affected from the soil moisture, but also from the texture, as well as any other obstacles, any other debris around. So there is this static component that will be fixed in the environment. There is also dynamic component. So with the machine learning tools, the idea is, can we just understand what is changing in the environment in this specific context? We are talking about the soil moisture, and can we then find out the correlation between the moisture as well as the signals, propagation characteristics, and then predict the next time what is the actual moisture amount in the soil. If you look at that signal propagation formula at a distance of t, you can see that it is, of course, affected by the distance, but as well as the attenuation coefficient and the phase coefficient, which are actually directly correlated with the soil's permittivity and conductivity, again, which are related with also the water amount in the soil. So overall, there we are expecting that there will be a correlation, but we need to, of course, sanitize that signal to understand the actual dynamic components effect. But Wi-Fi sensing is used for different purposes, like human activity recognition is one of the common applications. And then the existing tools most of the time just requires a network interface card. But this is one of the common ones that are used in current systems, and it needs to connect a computer to be able to extract that CSI information. Or you can use some more generalized, hardware like USRPs, which will be again not be possible to deploy in a scalable manner. So the problem with these existing methods, they either have a very high cost, or they will not be able to deploy it to a agriculture field in a scalable manner. To address that, actually, we look at if we can deploy a similar setup using the IoT devices, like microcontrollers, small low-cost devices. And then we found that these microcontrollers, which are ESP32 microcontrollers, specifically allows us to be able to reach out that CSI information, actually. And this tool has been around, and we open it to the community as well, and then the other researchers are also using it. There are a lot of attention received by that. And then our goal is to deploy these systems in the agriculture field, of course, and use it for soil moisture sensing. So of course, to be able to do that, we are talking about an outdoor environment, which is gonna require that we need to put some waterproof container, put them in waterproof containers, because their electronic parts should not be affected. So the way we did is we put them these as you see inside a waterproof container, and so that we can put some in all wild environments, but they need to also be powered. So for those we used some battery supplies, as well as in our experiments we also connect them to the smartphone so they can be powered. So in this specific case, we put them into a container filled with soil, and the idea is being able to understand the soil moisture most of the time using the loss signals. But as we will be seeing later, they will be also can be they can also measure the non-noise site based soil moisture when they are even next to each other. So these Wi-Fi devices in this specific case operate in the 2.4 gigahertz. And while doing our experiments with different soil moisture amounts, we also used some commercial sensors to get the ground truth, or we use some manual process. So since we started this project by the idea of is it really possible to be able to understand the soil moisture, the math shows that it's possible, right? But we want to start with some, basic setups. So after drying the soil in oven after during 3 hours, which is a very common process in these systems, when we divided into different containers, each included this much dry soil, and then in each of them we put some water, and in the initial experiment we started with the increments of 240 milliliters, and like this 240, and the next one is 2x, 3x, and 4 different containers. We collected our CSI data, purified it, then train our model with half of the data, then tested on the remaining half. So we have seen that we can really predict in a classification-based approach with the amount of moisture actually within those containers. So it was not also, by the way, it was not coming from the container differences, because what we did was we also tested the empty containers, and then the results were all similar. So it's because of the actual moisture amount which is affecting, the signal propagation. Again, the more soil, by the way, when we put this much water in the soil, we mix them thoroughly. So make sure that it's homogeneous first, then we did these measurements. So getting some promising results, and this type of increments, we reduce that increments to 120 milliliters with six classes now, six containers, and we have seen that we can still achieve some good accuracy. Of course, there were some confusions, probably due to the data collection, problems, because once we reduce that further to the 60 milliliter, we have seen that those numbers are really high. Still some confusions, but probably with more data collection, they can be also mitigated. So having these promising results, where we then look at uh, more long-term measurements, where we also get the actual ground truth data from actual sensors. So in this setup, again in a lab environment, what we did was we have the transmitter and receiver on the sides, as well as we have capacitance sensors here. In this case, we use three of them because these sensors were also not very reliable ones, and we were trying to get the average of them because the results were even for the different ones were different, so the idea was let them run, and then we will be collecting CSI data for 30 seconds for in every hour for 5 days. And we initially put some water and mixed that homogeneously as well. Then to speed up the drying, we put a fan, so which help us to dry the soil much quickly. And during that 5 days period, we noticed that the capacitance sensor values increased from 300 to 350, and which means that by the classification approach, we are actually getting like a 50 different classes. And then we trained our model the same way we did in previously, but with 50 different classes. And we have seen that if you want to get like a exact accuracy of what is the actual capacitance, which is of course correlated with the soil moisture amount, and we have seen that around like maybe 70% accuracy. But that was because there were some confusions between the neighboring classes, and then once we give some flexibility in terms of error, because even the capacitance sensors were having some differences in their values, we have seen that if we allow like the predictions with the just nearby one with error of 1, we can reach up to 90%. If that error goes up to 5, error margin allowed goes up to 5, we can achieve close to 97% accuracy. Again, these could be because of the some errors in the way we got the ground truth. Because next, what we did was we put this system in actually outdoors in not a real field, but in a garden, where we had like the same measurements during 2 weeks. But in this case, we wanted everything to be more natural, where we also use more commercial, more reliable, currently one of the traditional but more reliable and commercial sensor to get the ground truth. And we also let it dry by itself, also get extra moisture with a rain event. During these 2 weeks, actually one rain event happened. And in this case, also we switch our modeling from classification based to more regression based modeling. So as you can see, this type until here, we use the data for training, and then for that part we use for our testing portion. So we have seen that our predictions are, in this case, were very close to the predictions. Again, these are more predictions at every 1 second, but if you take an average over a window, that will be going also much lower, and you will see a very trend line very close to that. And then this is also can be seen that the average error was very close. So there is this hope like that we can definitely understand like the soil moisture in the soil, but then the question is, can this be generalized, right? So maybe it's specific to environments that we tested, and because they're in the soil, there are other things that we need to take into account. The one of the most important one is the soil texture, right? Soil is very complicated, thing. As you can see, different textures can be there, and then essentially this triangle shows the what we call soil texture triangle. A soil texture can be obtained with different mixture of the clay, sand, and then the silt component. So depending on the different amounts of mixtures, you can get a different names for the soil texture. And when then, as you can imagine, the water amount that are observed in these different textures will be different, so they are drying up, or maybe when it rains, the speed of their the moisture holding will be different. So we need to know actually, if we want to develop a more generalized solution, we need to understand the soil, so textures properties, and how it's also related to moisture holding capacity. And on the other hand, we also need to understand for different TX and RX installments in our system at different depths, or between when there's a different distance between them, the result will be affected. So if you want to develop a generalized solution, we need to be able to understand each of these features, as well as the soil moisture, which will be directly related to these, because our CSI measurements will be affected with each one of those. So with that, we started to look at the different things that we can do with this system. So initially we look at how can we understand the depth of these our system. Like, so specifically in this setting, we did place the RX receiver on above the soil, and then TX inside the soil. So you can think about this one as like separate device. The ones inside can communicate with the upper one to send their data, whatever their measurements. So in this case, when the RX and TX above and inside the soil, we got data with different depth levels, like 10 centimeter, 20 centimeter, and 30 centimeter, for two different textures, silt and sand environments. We can see that it's kind of expected, of course, because of the distances directly affects the CSI or an RSSI results. We can understand the depth of the device the device installed with a high accuracy. That's also same with different texture. But what we did further is, when we put them together, all these data together for two different texture environments, can we still understand what was the texture and what was the distance? So the results shows that yes, we can understand that they are installed in this specific texture, in different at this specific depth level. So we also further look like what's the if the distance between these RX and TX devices changes. Of course, the results will be changes because the CSI will change. Can we first understand the distance? From there, we can use a model specific to that distance, let's say. So for that, we installed these RTX and RX devices inside the soil at a fixed depth first, and then we look at the different distances between them, up to 50 centimeters for 6 classes. We can also see that for different like textures, soil textures, we can understand and where the distance between these devices very clearly. Even again, taking this further, with bringing everything together, we can see that when you put these TX and RX devices again on two different textures, you can also still understand what's the texture for a given distance. So the idea is under recognizing these distances and all other like textures and all other features in the soil first, then use a model specific to that type of setting, so that we can understand that soil moisture amount very accurately. So I would like to mention one specific scenario over here where you see that the TX and RX were actually there was no distance between them, meaning that they were next to each other. There was no soil in between, and ideally you're expecting that TX and RX will be communicating directly, but as they reflect from the outside the surrounding soil and then come back to the receiver side, you see that we can still understand the soil texture even in this scenario, because this is basically showing that our non-line of sight based CSI data collected will also help us recognize the texture in the soil very properly. And these numbers can increase if you collect more data and you use more complicated deep learning models, but our focus was to get the initial results first. So we look at the two different textures before, sand and silt, right? But as I said before, that soil texture can be more complicated in the field, and that's why we want to look at more complicated scenarios, where we started with in this soil texture triangle. uh, with different accesses. Like in this sealed separate access, what happens is it's a mixture of different amounts of sealed and in the clay, right? So we obtain the classes over here and then look at the binary classification of different textures. Can we identify? Let's say in this case, we can see that when you have a clay soil and a sealed soil with two same setting, or with ETX and RX, we can see that we can understand what was the texture with a very high accuracy, 100%, right? But as we go, like the very nearby classes, as you can see, this especially let's say sealed clay and clay, which are just neighbors, will be creating a problem, and then our predictions will not work perfectly. So, but that doesn't mean that our system will fail over here, because the soil moisture holding, like maybe for these two nearby textures will be similar. So we don't really need to differentiate these every type of, textures. Looking at the sand separate, we see that sealed in different mixtures of silt and sand, and we have again a much better scenario here as well. With also with two further classes, we can understand them very high accuracy, but the others are also much better compared to previous scenario. In the clay separate axis, and where we see that now even the further classes now has the issue, and it feels like because the clay is creating the problem in this setup, and it is even can be confused by sand, and when different also different other classes, other even they are nearby or further, is affected in this scenario. So for these scenarios, understanding the soil texture, uh, we might need further research on that, or we should also look at the the soil moisture. Like when we call it the CSI, to understand the soil moisture in the different textures. Maybe the model obtained in clay might work on the sand directly, so we don't need to really understand the difference between them. So after texture, now as we coming back to our original goal, where we were trying to obtain, like a very high resolution map of the soil moisture in the field, we wanted to look at when we form a mesh network with these and set up with all these TX and RX devices in the field, can sense the area between them for every TX RX pair within the communication range of each other, right? And they can also send their sense data to the others through Wi-Fi. So Wi-Fi can be used for both sensing between the other devices, every pair of devices, as well as sending their sense data to a central point. But it was so initially it will be hard to deploy such a system in the field. So we started with some kind of emulation, a mixture with the simulation and the real data, real measurements in the field. Meaning, what we did was how when we put these TX and RX devices in the actual field, and then what's the maximum distance that they can communicate, and what's the maximum distance we can actually get some CSI data. So we put them under the soil, also the above the soil, overground and underground. As you can see that up to 5.5 meter on when they are underground, we can still get some data like the CSI data at a fixed rate that we sent it the CSI frames to the other side. So knowing that maximum distance between these TX and RX devices, we tried to simulate some coverage idea for the mesh network setup. Remember, in the traditional sensors, what happens is you can only sense the surrounding, let's say a circular area with a radius up to something less than 1 meter, but this is very high actually. So if you add more sensors, what will happen in the traditional sensor cases, your coverage will increase just linearly with the sensor count. But with our setup, since we are trying to, sense the area between these TX and RX devices up to 5.5 meter, every time you add a new sensor or new TX RX device, which can be linked with other devices in different times, of course, you can actually increase the coverage exponentially. So with this addition of this new device, what happened is you added this area and you added this area to cover, the more areas. So what we simulated is, let's say, in an area of 18 by 18 meters, and with 16 of such devices, as with when they assuming that they can communicate up to 5.5 meter from our empirical measurements, right? And which when they cover a like elliptical area, like here as the sensing area, as they get close, of course, some of them will be linked because they will be getting to the range of each other, so they can communicate, they can sense the area if their distance gets closer than 5.5 meter. But as they get close, there will be some overlaps, right? So when you make them very close to each other, the sensing area will be getting smaller, and there will be a lot of overlaps. So our idea was, what is the, how the sensing coverage with these sensors will be changing when we use different distances between these devices. So we structured them in a grid based structure like this, when a 4 by 4, but we just reduce the distance between between the neighboring ones. So with that, what we have seen is, let's say, in a traditional sensor, what's happening is, of course, you have a circular area up to 1 meter. That means as the distance between them increases up to 1 meter, the coverage area will increase. But after 1 meter, what will happen is it will be static, right? But in our case, since we cover, as they get close, as the distance between them increases, there will be less overlap between the sensing areas, and you will be able to cover more areas. But after some point, there will be some link breaks happening, so the coverage will go down again. So this is what was happening over here as the distance increased and the overlaps decreased, and then now there was some link breaks. Then, but still, as you continue increasing the distance between them, the sensing coverage increase again, the overlaps, even with the fewer number of links, because the overlaps will reduce as the distance goes up. But after some part, all the distances, all the links will be failing, and it will go down after 5.5 meter. Remember, that was the maximum distance we assumed. So, but overall, we can reach up to like 25 percent of the coverage of the area, while the traditional sensors can only cover 4.4% of the area with the same number of devices. So that's the benefit of our system. Of course, our goal is be able to test this such a system in the field. But I would like to also mention in the remaining a few minutes some related ideas what we are doing currently. So we can, beyond the soil moisture, of course, we can also understand some other features. We want to explore because the soil salinity is also affecting the soil moisture amount. And can we also understand the soil salinity is basically referring to the amount of salt in the soil, and which is also another critical factor. We started looking at that. Also, we look at, can we understand the temperature of the environment, or in the soil, or in another medium. We didn't do it in the soil, but I would like to give some results regarding our recent data, our recent experiments in the liquid. So we were trying to understand the temperature of the liquid inside the container. We put out like a hot water, which around 85 Celsius, and it was going down like around 50 Celsius. And we had the TX over here, RX over here, which are outside. And we had also, for the ground truth, we have a sensor for understanding getting the ground truth, and also labeling our CSI data. So as you can see over here, for the 4 different experiments, there is a high correlation of the CSI amplitude with the temperature of the liquid over here. So if you do that in the soil, which was harder, that's why we started with the liquid case. There is a possibility that you can understand the temperature of the soil, which can also be affecting the moisture amount. So actually what we did is, with the case of the liquid over here, we didn't just use like a just simple machine learning model, because now we're talking about the temperature. There is some physics involved there, where we included the limitations of the rate of change in the temperature using the Newton's cooling law, because it says that there's like, as the time passes, and as you know, the environment, like ambient temperature, the rate of the decrease will be limited with that rate coming from the Newton's cooling law. And that's integrated to our model. and we tested our system of like predicting the soil, predicting the liquid's temperature in water, in milk case, or with different size containers, not just this one. And we have seen very accurate results actually. As you can see, the result in the water case, we can predict by just using the CSI value between a TX and RX, what is the actual temperature of the that liquid over there. So that was just a add-on to our soil moisture case, but again, this can be done in the soil environment as well. So as a summary, in this talk, I talked our exploration for understanding soil moisture and also texture using Wi-Fi signals. Our idea aims to develop a low cost and a scalable solution where you can collect the data and then send it to the those VRI systems to generate more accurate prescription maps, which can then do a more efficient, irrigation in the field using those central pivot irrigation systems. And then since we set different other features in the soil like texture and then deployment characteristics, deployment settings like the distance between TXRX will be affecting the results. Our goal was to develop a more generalized solution. We are still working on that side, but at least we have the components where we know the effect of different features in the soil. There was also this energy harvesting component. Since this project is a collaborative project with my colleague from UVA, and they were looking at that energy harvesting side, where our goal was we make these systems, DXRX devices, not just depend on the the batteries we have been using, we will be using while deploying them, we to harvest, also to harvest energy from the surrounding. And for that we actually propose to use the microbial fuel cells. And then that's something that, as I said, my colleague is looking at that. But by these devices are already actually can run without that up to 6 months with that with the measurements and with based on our calculations. We are just trying to increase that amount. And our future goal is actually by bringing all these together and also doing a large scale testing in the long term in the field once we have a prototype with all these components in the field, so that we can understand the effects on the those irrigation systems. So that's the end of my talk.